Welcome everybody to the virtual seminar Machine Learning Needs Mathematical Optimization. So this is the last seminar of 2021. As you may remember, we started back in January, and today we close the second season with Coralia Cartis from the University of Oxford. And before I briefly introduce Coralia, I would like to announce that we will be back in 2022. We will return with season 3. You will receive more news if you are a member of our mailing list, or otherwise you will receive also the announcements in social media. So we have the pleasure of showing you some of the people that have already accepted. So you can see that we have names from the operations research community from Europe, but also from America. So we are very, very happy that they have already accepted, and more details will be coming. But today we are back to the seminar of Coralia Cartis. We are very pleased to have her. She is an associate professor in numerical optimization at the Mathematical Institute at the University of Oxford. And she's also a tutorial fellow in mathematics at Balliol College. I must say I have the pleasure to have known Coralia for quite a while when we were there in Oxford together. She is also an Alan Turing Institute Fellow, and in 2018 she became a member of the scientific board of the Smith Institute for Industrial Mathematics and System Engineering. The research of Coralia covers algorithm development, analysis and implementation for a variety of problem classes: linear, convex, non-convex, smooth, non-smooth, stochastic, and they are suitable for larger scale optimization. She has worked on applications such as compressed sensing and sparse approximation, but also climate modeling. She has published at top journals in our area, such as Mathematical Programming and Design Journal on Optimization, to put a few examples. And she was actually the plenary speaker at the Euro conference in Athens back in the summer. So we are extremely pleased to have you today, closing our second season. Thank you very much.
Thank you very much, Dolores, for this very nice and kind invitation and introduction. Is this okay? Can you see the screen and everything?
It will take a little bit, but yeah, I will let you know when you are sharing the content. Yes, I can see it now. And I will remind the audience that we follow the usual rules. If there is a very, very urgent question, please put that on the chat. Otherwise, Coralia will answer all the questions at the end. Thank you so much.
Great, thank you very much. So today I will speak about different strands of my research that come together under this umbrella of optimization for data science applications that were inspired by these applications. And different parts of this work I joined with my postdocs and PhD students, Yari Folks and Estelle Marsar, my postdocs, and Adile Osemisov, Alex Puyu, and Zhen Shao, my PhD students. So I will briefly remind people about the challenges we face from machine learning problems, and then about a useful tool that we have that we can do to reduce the huge dimension of these problems and how we could make use of it. So this tool is from randomized numerical linear algebra, and how we can make use of it in improving the performance and the design of optimization algorithms, both for local and global optimization. In all this, I hope that I can illustrate the benefits of having adaptive algorithms, having second-order information, and also being able to reduce the scale of the problems. So just to remind people, things they are in this seminar series quite familiar with, we want to deal with data. We want to classify data. For example, in binary classification, we want to assign labels to given input. And for that, we do supervised learning, where we choose a class of models, and then we use some label data, some training data, to find the parameters that best fit the data, the parameters of our model that give us the model that best fits the data on this kind of scene data for which we know the labels. And for this, we minimize, for example, we construct an auxiliary optimization problem in which we minimize, for example, the average number of mistakes that we make. And when we formulate this in terms of an expectation, we would need to know the distribution here. However, that's usually not possible, and so we simplify this problem to minimizing so-called, instead of the expected risk, the empirical risk, where we just make it discrete and choose a finite random training set, subset of the training set typically, and then we minimize this, again, number of mistakes in this average number of mistakes in this training set. However, this is an indicator function here and there, really, where we quantify mistakes in terms of this product of the yi label times the model output at the input UI. And so if this has the wrong sign, then we count it as a mistake. This, being an indicator function, is non-smooth, and we don't really like that. And so we again simplify this further and turn it into a smooth problem. So we smooth out this indicator function through some kind of loss, logistic or regression loss, so that what we end up with is minimizing this, in quotes, easy sum of functions, where each term in this sum of functions is a smooth term depending on our training data and on our family of models, and also the number of terms in the sum is to do with how many what sample do we choose from the training set. This was just a linear case of binary classification. However, now we want to deal with the very powerful deep neural nets, where instead of our models being some linear hyperplanes that classify points, now we have more complicated functions that are compositions of affine functions with nonlinear activations. So our models, our predictors, are now these compositions where what we want, where we start with the data points, and then we compose them through, for example, through this function phi that are, for example, the ReLU function, the max of 0 and the argument. And what we want to find here is the weight matrices AJ, these are the unknowns, and the biases BJ. And so through this composition, through these different layers, we end up with our model at the final layer. And so the parameters we find in this model are indeed all these matrices, weight matrices, and the biases. These are the ones we try to find in the training. And again, the idea is the same, that we are going to choose the function within this class of models, the model within this large class of models that gives us the best match of the predictor P at data UI compared to the labels we have yi. So again, we can use regression or logistic loss, and I've given the expressions here that you know well. And so again, here we minimize the sum of functions of these losses. The problem is, of course, that these problems are huge. They have millions of variables and terms in the training set, so millions of parameters that we want to find, and data points, namely the number of terms in this sum. It is, though, a deterministic problem, but if we really think about what we care about in these problems is we find a model, but then we want to use it for prediction. So we want to do well on the unseen data. So in other words, what we really care about is to minimize some underlying expected loss. We would like to do well on that. Of course, the usual approach here, the workhorse here has been stochastic gradient. And what we do there is to further subsample from within the training set. Some of our data points, some of our, in other words, functions in the sum of functions. So we are going to further randomly subsample and calculate the gradient only of those functions fi from the sum of functions corresponding to this batch, to these subsampled terms. This could be a small number compared to the size of the, it is usually a small number compared to the size of the training set. And then we are going to take a negative approximate gradient step along this, direction, where we cut it by a line search, as we call it classically in optimization, and people call it learning rate in machine learning. Usually this step size is predefined, so it's a constant step size or a decaying step size, and people typically have not spent, they spend time tuning it, but they don't spend time adapting it in the run of the stochastic gradient training. The other common assumption for the analysis of this framework, of this kind of stochastic gradient algorithms, has traditionally been that the batch gradient is unbiased, is an unbiased estimator of the true gradient. And from this kind of assumption, what one usually derives is convergence with positive probability of the expected value of the true gradient to 0. So we cannot guarantee that we don't have, we cannot guarantee typically almost sure convergence and just convergence with positive probability of the expected gradient. So the expected gradient goes to 0, so the probability is positive of having a convergent approach. Furthermore, so this is weaker than what we usually have. Furthermore, of course, we encounter ill conditioning. We can really only solve to low accuracy. What we would like to do is to propose methods that are hopefully scalable, but also adaptive in the size of the batch and in the size of the learning rate, knowing from classical optimization that these things work well in practice and that they can lead to better convergence guarantees, namely to almost sure convergence. But we would like to allow biased estimates. We would like to also allow errors and not require that the gradient is the batch gradient is unbiased. Hopefully, I get to talk a little bit also about curvature issues. Before I delve into all that, into our approaches, I would like to tell you a little bit about sketching and also some contributions we made to this area. So sketching is a tool from randomized numerical linear algebra, and it crucially relies on the following now famous lemma, Johnson-Lindner-Strauss lemma. It tells us about how can we project vectors from high dimensional space to a low dimensional space while preserving their length, and how much can we reduce the dimension of the space when we do this projection. So here's my vector x, a given vector in Rn. N is going to be our ambient dimension throughout this talk. And what I want to do is to take a matrix S that is underdetermined and use it to project, to get a vector S times X in a smaller dimension space in Rn. Now, what Johnson-Lindner-Strauss lemma tells us that if S is a scaled Gaussian matrix, where this small dimension M is given in this way, where delta S will be our probability of success, or sorry, in this case, failure, and epsilon S is the accuracy in the projection, is how much we lose in terms of the accuracy in the projection, then S will preserve the length of the projected vector. So the length of the projection will only change from the original length of X by a multiple epsilon S. And this is true with probability at least 1 minus delta S. First, I would like you to notice that this is a high probability result because delta S appears here in a log. So I could replace 1 minus delta here with an exponential, and I still wouldn't destroy my projection properties. The other thing to notice here is that this size of M, the size of the projection, is independent of the ambient dimension. So it does not have dependence on N, our large dimension N, in it. So I would like us to see how we can understand this result. If we look here in the plot, let's take first a random x. So if x is random, how could we calculate its length? If x is random, we subsample some of its entries and measure the length of those entries and then maybe normalize it. Okay. So if I do that and I choose a random x and then calculate s times x, where s is a Gaussian, and I scale it, I get this plot here for different vectors x. And what we see is that the length, that this ratio is essentially close to 1. And this is what Johnson and Strauss lemma is telling us, but also for deterministic x. So what happens when we have x deterministic is that we can view it as being transformed and then being treated as random. And the Gaussian matrix x both as a transformation and as a sampler. In other words, a random projection. So again, the size of the projection M for S, so the small dimension here, does not depend on the ambient dimension, and neither does the accuracy epsilon S. What happens though if I want to project not just one point or finitely many points, but a subspace, an infinite number of vectors? So let's take the column space of a given matrix A as our subspace that we are trying to preserve. So A is n times D, where n is still the large dimension. And D, you can think of D as the dimension of the subspace. Then, if I take S to be of size proportional to D, so the small dimension of S is proportional to D, then again I can preserve the length of any vector in the random subspace. Sorry, I can preserve the length of any vector in the column space of A, and with high probability. And these pictures here show us this kind of phase transition that happens when M is less than D. The length of the projected residual is large, but as soon as it's essentially D or larger, I can preserve it extremely accurately. I can preserve the length of the vectors. So basically, we have still in this, even when I project a subspace, I do not have dependence on the ambient dimension N in the size of S or in the accuracy. I do have the dependence, of course, on the dimension of the subspace. The problem with the Gaussian matrix, though, is that to form, for example, S times A, we need we regain the dimension, the ambient dimension dependence. So then we have N coming in. So we would like to use something else than dense projectors. We would like to use sparse projectors. Now, are there sparse projectors that come to mind? Immediately, subsampling. So if I have a matrix A to project it in a sparse way, for example, I could just randomly subselect rows of A. However, if A has some rows that are very important, when I do this kind of uniformly sampling rows of A, I may lose some important rows. And indeed, when S is a sampling matrix, so it has one non-zero per row, S will not be an embedding, will not be a Johnson-Strauss embedding unless A has similarly important row. We call such a notion as low coherence. So if A has low coherence, similarly important rows, then we'll get an embedding with sampling, but otherwise we don't. And there are theoretical results that capture this. There are better sparse embeddings than sparse random matrices with better properties than sampling. So instead of losing one non-zero per row, we could do one non-zero per column, and this is the so-called hashing or count sketch. And in practice, we have people have noticed for a long time that count sketch is much better than sampling, as has very good properties, embedding properties, very often as good as the Gaussian matrix. But theoretically, the bound was not as good. And what we were able to do was to improve this bound. Before I say that, let me just explain why hashing is better than sampling. So in sampling, we randomly subselect rows, but we may miss some important ones. When we use hashing matrices, and we have one non-zero per row, we may have we have more than one non-zero we have one non-zero per column, and so we will have more than one non-zero per row, and in that way we will touch all the rows of A. So when we form S times A, we will get sums of rows, and we won't lose so often important rows. And indeed, what we are able to quantify for hashing was to obtain that M can be proportional to D. Until now, people had D log D or other terms here. If A, of course, is not does not have terribly bad coherence. However, this M proportional to D for these matrices was not known. People were not able to obtain it before. Of course, we may have more than one non-zero per column and so on, but these hashing matrices work really well. Right, so this is the end of my detour. So let's come back to optimization. I hope that people can still hear me.
Yes, we do. Yeah.
Okay, great. Thank you. Right. So let's see where sketching comes implicitly into these frameworks that I've started my talk about. Well, we had our sum of functions. Now, when I constructed my stochastic gradient, we can view that as taking all the sums of functions, or taking all the functions in the sum of functions, and making a long vector out of them with entries fi, okay? And then applying a sampling matrix sk, m times n, so applying a sampling matrix to that long vector, the sum of functions, to give me my reduced function f for which I take a gradient descent step. So I can view my stochastic gradient in that way. In other words, I sketch in the data points with a sampling matrix. That is what I do at every step of the stochastic gradient method. We can do a similar thing for linear least squares or non-linear squares, and people have done that. One obtains stochastic algorithms. And basically, whenever you do subsampling in a sum of functions or a sum of term, you would do an implicit sketching with a sampling matrix. So this is in the observational domain, but we can also look in the parameter space, in the variable space. If we sketch in the variable space, let us look here. What would we do? We would replace minimizing a function f of x, where x is in Rn, with minimizing a function depending on a variable y, where y lies in Rm. And sk, of course, transpose here. So x, I replace it by sk transpose times y. So sk is still my underdetermined sampling matrix. If sk is a sampler, all I get when I do that is a random block coordinate method. So if I sketch in the parameter space, I end up with a random block coordinate method, especially if I use a sampling matrix. If I don't use sampling, I end up with some random subspace methods. So we can see that sampling sketching implicitly occurs in these methods, but I've just tried to tell you with what I've said before in my detour, that sampling is not such a good random projection matrix. It does not have such good embedding properties. And indeed, you can see that because for all these methods, block coordinates or stochastic gradient, the convergence is in expectation or with positive probability for a fixed batch size or a fixed block size. So the question is, can we do better? We know we have better embedding matrices. Can we get better guarantees? Other matrices are more robust. How can we do that? So for the rest of my talk, I will try to give you some ideas about how we can do that. And I will start with local optimization and obtaining random subspace methods. Mostly I will talk about how to sketch in the parameter space, and I will not talk much about sketching in the observational or the data points in the interest of time. So I want to sketch my variables. And so I take a standard, I'm going to consider here a generic approach from non-convex optimization. So I minimize my function f. I'm at some current iterate xk. How do we do that typically? Well, we think of most methods for non-convex optimization as associating to this function f a local model. So at every point xk, so this is before I do any reduction, this is just the usual approach. The usual technique is to approximate my complementary function f locally by a local model. So I have here a full model, like a Taylor-like model. I have here the gradient of f at the iterate, and I can have here an approximate second derivative matrix Bk, depending on how much curvature I can afford to calculate. So at every iteration, I would associate this local model. I would minimize it instead of my function, and then I would do a line search or a truss region or a regularization to constrain the length of my direction S and ensure global convergence from any starting point. That's my standard non-convex optimization algorithm. Now, what I want to do is to insert in this kind of methods reduced model. So instead of solving the full model here in the ambient large space Rn, I'm going to sketch my direction S. So my local model will be reduced, will be in my subspace Rm. So here's my S transpose. So S is my sketching matrix, and I apply S transpose. I use S transpose to sketch in the variable domain. So S is my original direction, and now I sketch it with a random matrix Sk. And when I do that, so I replace S in the full dimensional model by this Sk transpose S hat. S hat is in the reduced space. And when I do that, what happens is that I'm going to get here in this first order term, I'm going to get a reduced gradient. Okay, so I can use the transposition properties or the inner product properties, the adjoint, to get here a reduced gradient, transpose the reduced direction, and then a reduced second order approximate matrix here. So everything is now in the reduced space. So I solve a reduced model. But I want to emphasize here that when I write Sk applied to the gradient here, I don't assume that I have the gradient in the first instance. I assume that I only calculate some kind of actions on the gradient. So for example, if Sk is a sampling matrix, then I would just calculate some of the finite differences in the gradient term. So I try to reduce not just the calculation of the search direction to happen in a smaller dimensional space, but also that the problem information needed to form the reduced model is limited. So I don't calculate the full gradient. Of course, and then I would do the usual, I would enforce a line search or a learning rate or a truss region or a regularization. So what we do after we calculate this reduced direction and reduced problem information, we do have to project it back in the full space. And then we may or may not take this step or accept this step. We take it if the function has decreased when the model has decreased. So in this approach where I just deal with reducing the dimension of the variable space, I do assume that I have accurate function information. So if I will measure, if it agrees with the model decrease, then I take the step. Otherwise, I may change my algorithm parameters like the truss region, I shrink it, or the step size, I shrink it as well in line search, and then recalculate, stay at the same point and recalculate the step. Otherwise, I make progress and I may increase these parameters. So under what conditions on the sampling matrix can I guarantee that this algorithm is convergent? And what kind of convergence guarantee can I provide? I only need to sketch correctly the gradient and to have a bounded sketching matrix with high probability. Indeed, so I only need to preserve the length of my gradient, in fact, even just one-sided length. So I need a lower bound on the sketch gradient. That's a multiple of the true gradient. This epsilon s here is the accuracy, but I don't care if it's a half. It doesn't matter. It can be a reasonable constant there. So I require that my sampling preserves the length of the gradient and that it's a bounded sampler. Of course, in my algorithm, I allow the algorithm parameters to change. I allow them to adapt, and they will help me get out of problematic situations. But under these assumptions on SK, I can show that if my function f that I'm trying to minimize has Lipschitz continuous gradient and is bounded below and so on, then my random subspace trust region or line search or regularization method will have almost sure convergence. So the true gradient, at least one limit point will be stationary, will have the true gradient will converge to 0 with probability 1, the limit with probability 1. I can also bound the number of iterations required. So I can bound, I can get that the number of iterations required to get the true gradient, which of course I don't see, to get a true gradient below epsilon, the expected number the number of steps is less than a multiple of 1 over epsilon squared, a constant multiple, and this happens with exponentially high probability. This complexity bound here, in terms of the accuracy on the gradient epsilon, which is different than epsilon s, this accuracy is the small epsilon in this framework, and this bound of epsilon to -2 is what we would expect and what we get for deterministic methods that see the full gradient. So we actually recover the complexity of the deterministic variance when we have full problem information. This complexity deteriorates by a constant multiple that depends on the probability of success of correctly capturing the length of the gradient, the success of the sketch. I also need to be a little bit careful here when I design my algorithm. I have to make sure that there is an interplay between how fast or how slow the trust region or the line search increases or decreases in the algorithm compared to the success probability. But the success probability I can design. I assume I can design it, and also the algorithm parameters. There is no unknown, Lipschitz constant dependence or things like that. But I have to make sure that I don't shrink, for example, the trust region too fast if I don't see good models, good length preserved gradients often enough. So this comes in, but I can ensure almost sure convergence. I also want to note that we allow biased estimates here for the gradient. I only require length preservation, so the entries themselves can be wrong. And I also allow inaccuracy. I only need a one-sided inequality, and I allow epsilon s inaccuracy in it. Let me tie into what we saw about sketching earlier. When will this sketching condition be guaranteed with probability 1 minus delta s? I only need to embed, as I said, a one-dimensional subspace correctly. That's a very weak assumption. I started with that in the JL lemma, in the Johnson-Strauss lemma. There is no ambient dimension dependence. There is no n dependence. So SK, the Gaussian matrix with size m, this will work. Hashing matrices will work. And they allow me, these sizes here, essentially because delta s and epsilon s I can choose, they allow me to choose a fixed block size, essentially. Random subspace, fixed dimension. I need to be a bit more careful with my upper bound on the sketch, and there I will have a fractional dependence on the ambient dimension. So an n over m, a square root of n over m dependence. However, this matches, if you think that you don't see problem information, this would match with what we would get if we count as n having full gradient information. Now, what happens if SK is a sampling matrix here? Well, we don't have such properties. I cannot have a block coordinate variant with a fixed block size with almost sure convergence, only if I have the right problem assumptions. So in other words, if the function f that I minimize has a gradient with entries that are not too dissimilar from each other, so the finite difference terms in the gradient have similar magnitudes, in that case, I can give almost sure convergence for block coordinate gradients, but otherwise I cannot. So the properties depend on this kind of coherence of the gradient. So we can see, as we know, that random subspace methods have that other samplers are other random projectors are better than sampling matrices. We can see that coming in. I don't want to spend a lot of time on how do we prove this, but basically the idea is how much inaccurate information can a standard algorithm tolerate. So if I take a non-convex optimization algorithm, how inaccurate can my problem information be at each iteration so that I still ensure almost sure convergence? We use the framework of probabilistic models here, because that's essentially what that framework does, is to address this question. So this local model I construct is good with a certain probability, sufficiently accurate, but can be arbitrarily bad otherwise, allowing bias. And how we counteract this kind of inaccurate problem information is by having an adaptive algorithm parameter, so that we allow it to recover from bad situations, and by tying the success probability of these models, of seeing good models, to how fast or how slow we decrease these algorithm parameters. The analysis is complicated, but it can be done. Okay, I want to move on a little bit. So using this kind of general framework I presented, we were able to design, for example, Gauss-Newton methods. So if I take nonlinear least squares, we now reduce the size still of the variables in there. And in Gauss-Newton, for example, what we do is we linearize this nonlinear term at each iteration. So usually we would have a Jacobian times the direction plus the residual, and we would minimize the Euclidean norm of that. So we have a regression, a linear least squares that we solve at each iteration of trying to solve my original nonlinear least squares model. And what we can do with this framework that I proposed is that we do not calculate the Jacobian at each iteration accurately. For example, we would calculate only some columns of the Jacobian. So I would only do, I assume that, for example, I am able to have all my observations, but I would only calculate a few finite differences of my observational terms. For example, we use this in climate modeling, where for every finite difference of my to calculate a finite difference of the climate model, I have to run the model with a perturbation of the parameter. So this reduces the number of model runs that I have to do, of the climate model runs. And of course, we can use this in other frameworks as well. We used it in derivative-free, etc. So we save on Jacobian calculations, and we get almost sure convergence with some random ensembles and otherwise, as I've explained. We have done some numerical experiments on with logistic regression on some simple data sets, chemotherapy, GZ, and so on. And what we measure, what we notice, so here we just did blocks of the Jacobians in this Gauss-Newton framework, and I just want to illustrate to you what we notice when things work well is in terms of iterations. Okay, if I run a full model, Gauss-Newton model, and I have the Jacobian, then of course I take few iterations on this model with the full model. But when I go to having a reduced model, I'm going to have more iterations of my algorithm. However, when I look at runtime, to do one iteration of Gauss-Newton method costs a lot more, or a small number of them costs a lot more than doing many of my random subspace Gauss-Newton approach. So you can see here that in terms of runtime, we win. And we also win in terms of how many finite differences I calculate. So how many Jacobian estimations I do, Jacobian actions I do. That's also what we gain in. So this is what we see when things work well. Sometimes, of course, these methods can be slow, but and you need to enhance them a little bit. But the basic concept is that you would gain in runtime, or you would use them when you cannot use full size models at all. We can do second order methods, but there it's more involved. We've also extended these approaches to the FO, and we've done a lot more careful algorithm development there. This paper is out. I have not talked about sketching in the observational domain. There is a vast literature that looks at adaptive subsampling in the observational domain, and how to do that and get almost sure convergence, how to do complexity, how to also with almost sure convergence. So I've cited some papers there. There you lose accurate function information, you get stochastic algorithms, so things are also challenging from that respect. Now, I would like to go on to talking a little bit about global optimization and random subspace methods for global optimization. So I want to minimize my function f, and what I've talked about until now was to just I just I have a random subspace, and then I solve in that random subspace locally, and then I move to that point, and then I solve again, and I locally at each step. Now here, and then I obtain a local solution. Now what I want to do here is I want to minimize globally in each random subspace. So I do want to find the global solution of my non-convex problem, not just the local solution. We've addressed this in both the unconstrained case and the constrained case over a box domain, but for simplicity in this talk, I will just address the unconstrained case. So the framework, as I said, is simple, and I can only do this for global optimization for the Gaussian, for a Gaussian embedding. So I have my iteration is the following: that I'm at a point, I draw a random Gaussian matrix, and then I solve my problem in that subspace globally. Approximatively, even with some probability, numerically I can solve it locally, but in theory I have to solve it at least approximatively, or at least with some probability globally. So I minimize over y in the subspace, and I'm also allowing myself some flexibility in terms of the anchor point at which I draw the random subspace. In other words, once I've solved in a subspace and I found a good point there, I move to that point and then I draw my next random subspace at that best point I found so far. I can do that. If you don't want to do that, you just set this pk to be the origin, and then you just keep drawing the subspace at the same point, or you can use some other predefined strategy. This framework allows a lot of flexibility. Right, so I draw random subspaces and solve globally in each subspace. Now what I can show is that if f is Lipschitz, and we solve to sufficient accuracy in each subspace, though so I have to guarantee this at least with some probability, and for a variety of anchor points for my subspace, we can show that these major iterates, namely these points xk that are the minimizer in the subspace, of course projected back in the full space, they will enter a neighborhood, epsilon neighborhood of a global minimizer of my problem with probability 1. So again, almost sure convergence. How did we show this? We went beyond sketching techniques. We had to go beyond sketching techniques. Basically, we had to assess what is the probability of success of a random subspace hitting a ball around the current, around a minimizer x star. So I have a global minimizer of my problem x star in blue here, and then I have an epsilon neighborhood of it. And what we want to ascertain, what is the probability that a random subspace drawn at some point P intersects this ball? It turns out that if we rephrase this question in terms of cones, so we can look at the circular cone generated by this ball and the anchor point P, that gives me a deterministic circular cone. And then I treat this random subspace drawn at P as a degenerate cone, random cone. Then I'm looking for the probability when this random cone intersects, shares a ray with a deterministic given circular cone. And people in stochastic geometry have quantified this probability. So we use the results using conic intrinsic volumes. and Crofton formula and so on to quantify this probability of success. Of course, it depends exponentially on problem dimension here, on the ambient dimension, because this is still the general case here, general non-convex global optimization, so it's NP hard. However, this bound is better than, for example, uniform sampling and simple random search. Okay, so this is for the general case. But really, what I want to tell you a little bit about now is when would such a random subspace be particularly useful for global optimization? When we have a special structure, the following. So basically, we assume that there is an effective subspace in which our general f varies. In other words, I have a function like this sinusoidal surface here. This sinusoidal surface only has something interesting happening in a certain direction. There is variation in it over which I need to optimize in a certain direction, but it's constant on directions orthogonal to my direction of variation. In other words, if I knew this subspace of variation, I could just solve my global optimization inside that, and I would be done. So this function only varies in a low-dimensional linear or affine subspace of dimension, say dE. We denote it by dE. Where is such a structure found? In over-parameterized systems. When you have a lot of parameters in a system, it is natural that your model, your system, will only react to changes in some of the parameters, and some of the remaining parameters are in some sense superfluous. Now, are these effects linear, which is what we assume here? Of course, that's not always the case. But it is often the case, or it is approximatively the case. So we studied here this idealized setting where we assume that these changes are happening in a linear subspace to see what happens. Well, let me just illustrate. So what happens then is that for every global minimizer, I will have a subspace of global minimizers that are present. And it follows then that if I draw a random subspace of dimension greater or equal than my effective dimension dE, so if m is greater or equal than dE for my random subspace, then with probability 1, my random subspace or random line here, the red line, will intersect my blue lines of minimizers, of global minimizers. In other words, I draw a random subspace and I do a global minimization in it, I will find a global minimizer of my problem, provided this random subspace is large enough. Of course, this is only true in the unconstrained case. So, of course, the interest here is I don't know this effective subspace. If I knew it a priori, I should just minimize in it. But if I don't know it a priori, but maybe I have a sense of what its dimension is, then it's enough to draw a random subspace and solve once in it. Indeed. So in this random subspace that I started with, I said you draw a random subspace, you minimize in it. Well, if my function f has low effective dimensionality dE, and I know this dE, then I only need one random subspace. So I only have one major iteration of my algorithm. And the size of this subspace only depends on the effective dimension or a bound on it, not on the ambient dimension. If I do not know dE, but I have this unconstrained problem, then what I do is I can start with some small dimension sk and keep increasing it. And as soon as I've reached a dimension for my sketch, for my random subspace of larger than dE, the algorithm will make no further progress. So whether I know dE or not, in the unconstrained global minimization case, where f has this special structure, I will have finitely many random embeddings needed to solve my problem globally, and there will be no ambient dimension dependence. And you can see this with simple experiments. What I can do is I can run this random subspace, where, for example, with Baron. So I take a global solver, standard. I apply it to a global optimization test set. I take a standard test set, and then I infuse it with this special structure. Basically, I take every one of these global problems, and I add spurious dimensions to it. I add zeros. I assume that it is much larger in dimension than what is given. And then I rotate these spurious dimensions that I add. I include a random rotation so that my effective subspace is not aligned with the coordinate axis in every example. So I do that. So my test set will have this special structure, but I will not tell the solver what is the effective subspace itself. Only I will assume I know the dimension in this experiment. And you can see here that what I do is I increase the dimension of this test set from 10 to 100 to 1,000. And the probability of success of finding an accurate global minimizer does not change for the case when I randomly project and then solve with Baron, compared to the case where I don't do any random projections and I just solve these increasing dimensional problems with Baron directly. So Baron decreases in performance with increasing ambient dimension, but these random projections approaches stays the same, and every solution just needs, every solve just needs one random projection. We've observed similar performance for other global solvers. We can use local even, numerically at least. We cannot guarantee that theoretically, but practically we did, for example, nitro. Nitro has a local and a global feature for the solver. And when we apply it, again, the dimension, the n is big D here, this grows. And what we see is in black is the no embedding framework. And this decreases in performance in these performance profiles, while solving a random subspace approach with nitro globally is better for large dimensions, and solving it locally is even better. When you solve locally in every subspace, you have to be a little bit careful because you may stagnate, but then just draw the subspace at a randomly chosen point. That's what we do in the code to get this performance here. Why would we care about this special structure? Well, as I hinted, and random embeddings here. So as I hinted earlier, they do occur in these over-parameterized models. And I want to tell you a little bit what inspired us in this work. We were inspired by a Bayesian optimization paper of Wang and De Freitas and others, where they enhanced the scalability of Bayesian optimization solvers using embeddings. What we tried to do in our framework was to say, well, you don't really have to do Bayesian solvers. You can use any global solvers combined with random embeddings to improve scalability. Also, their theory is when the effective subspace is aligned with coordinate axis. And what they did in this paper is to conjecture that this low effective dimensionality structure is prevalent everywhere. And this kind of random subspace frameworks would help even if you don't know exactly that it's present, or if it's present even if it's not exactly a linear subspace of effective dimensionality, but an approximate one. Similarly, in a paper of Bankstra and Bengio, they suggested that instead of very involved tuning for hyperparameters for machine learning, one can do some kind of simple random search. And also they conjectured there how only very few parameters, how only a few parameters would matter in tuning and training. So there they look at random search versus grid search and then some simple procedures. So in many of these papers, this notion of low effective dimensionality of an objective is very prevalent. Furthermore, for deep neural nets, people have taken the parameter space and done a random projection of the parameters and the weight matrices and the biases, and then just solved one random projection of for the training. And what they have noticed is that they get good accuracy. So you can do quite a substantial reduction of the parameter dimension and still get decent results. So again, in these papers, this notion of is there low effective dimensionality present there? It seems that it is. What we have tried to rigorously quantify and prove mathematically in our framework for global optimization is to show that indeed, if such structure is present, a random subspace framework will give you almost sure convergence, will not depend on ambient dimension in the unconstrained case. And so this notion of low dimension present in deep neural nets is quite an important timely question that people are trying to answer. I will stop here. I wanted to talk a little bit about first versus second order methods, but I can stop as I'm out of time.
Thank you very much, Coralia. It has been really great to have you here. I will open the floor for questions that the audience may have. And I'm sure that we will be thrilled to invite you back to talk about the slides that you couldn't cover. Are there any questions from the audience? I believe you should all have the right of, I'm muting and sharing your video.
Should I stop sharing?
I think it's fine. Oh well, if you want to see the video, yes, you should do that. Yeah.
Hello,
yeah.
I have a question. Thank you so much for your presentation. Can you explain a little bit more Johnson Lindenstrauss lemma again?
Yes. So okay, maybe I should share my screen. Okay, just okay. So basically, in Johnson-Lindenstrauss lemma, so this fundamental result in randomized numerical linear algebra allows us to project from high to low dimensions while preserving the length of vectors. So basically, this is the property here, okay, that you get from it. So you need a random matrix of the right size, okay, but then you can guarantee this property. Now, what I want to emphasize here is that so you have A is given. So you have A, and then you draw the matrix S randomly, and then with high probability you won't see bad cases. The length of the projected vector will only be distorted by plus minus epsilon compared to its original length. I'm not quite sure what else specifically you would like me to explain.
Thank you. That's it.
Thank you for your question. So I would recommend. So for example, there are several surveys, but for example, Woodruff and Clarkson, they have a randomized numerical linear algebra survey. It's called Sketching Tools for Numerical Linear Algebra, something like that. Also, Michael Mahoney has a very nice survey on this topic, and it's really a very nice, fascinating area.
Nagisa, would you like to ask the question? I believe that you have the right to unmute.
Hello, I hope you can hear me now.
Yes.
Okay. Thanks for the presentation. It was very exciting talk. I wanted to know about the very last topic. We have like a random embedding, and our discussion was like if we know the effective domain, effective kind of dimension, we can have like a sufficiently large random embed kind of projection, and we can solve it. And if you don't know, we can start with the small, and we can increase iteratively, and we can hit the kind of large enough projection, and we can terminate. I was thinking, is it do you think it's sensible just keep the projection dimension small, but like a repeating sampling? Because I was thinking maybe we can say very likely we find a solution enough, not very large number of iterations, even projection dimension is small enough. If we sample many times, we find global solution. And I was thinking we can bound how many we need in probability.
So it is possible. It is possible because you would fall under the case of the general objective then. So you would not very much exploit the structure enough, because the way to think about this is that we think of DE as a small number. You know, DE compared to this effective dimension compared to the ambient dimension is very small. So you would not have to do a lot of embeddings if you were to grow the dimension. You know, if you do not grow the dimension and keep it fixed, and you have underestimated, if you have underestimated your effective dimension, then you are still guaranteed to converge, but you will converge much more slowly.
Okay.
Because the first thing I mentioned was we have a general non-convex problem, and we want to quantify a random subspace for global optimization method for global optimization. Yes, we have almost sure convergence because of these conic bounds that I mentioned, even if you don't have special structure. But it's going to be slow. It's going to be slow. But if you have a special structure and you allow it to increase, then you are much better exploiting your special structure.
And also, like, if we increase and if we didn't see the improvement, we can kind of conclude we found
exactly.
Exactly. So it's kind of much better in that.
Yeah, exactly. Now we've also quantified all these bounds when we have a box, and when we have a box domain, then of course so if we have effective dimensionality, low effective dimensionality, but over a box domain, then you start seeing the ambient dimension coming in, but it's still not as bad as if you have no special structure. So we even were able to prove polynomial complexity then in terms of the ambient dimension, but you see it coming in, while if you have an unconstrained problem and effective dimensionality, it's free of the ambient dimension. So we have these papers are out, and they are with Massar and Otevison. Yeah, so you can find all these results out.
Nice. Thanks.
Yeah.
Thanks for explanation.
Sure, my pleasure.
Thank you very much, Nagisa. Are there any other questions? I don't think I see any other questions. So, Coralia, thank you again so much for coming so late in the year. I mean, we are all preparing to have a little bit of a break, yeah? So you now deserve it even more, yeah?
Thank you so much. Yeah? Thank you for everybody. Thank you so much for being here at this Christmas edition. Thank you very much, and I wish everyone a happy, peaceful Christmas and holidays. Thank you.
Yeah.
Thank you.
Yeah, have a peaceful Christmas.
So
thank you so much.
Good health to everybody. Good health to everybody.
Yes, yes. Take care, everybody. Thank you.
Bye.
Thank you so much.